Hi everyone, welcome back to our seminar, and today Godsil is going to tell us about Laplacian state transfer.
Thanks, Mary. Okay, so what I want to talk about, well, I want to sort of, in certain sense, explain how we got to this. We were thinking about, well, generalizations of the usual versions of continuous quantum walks, and so we led to these problems. And then that led us to a bunch of, well, problems in spectral graph theory, which in principle could be stated without any reference to state transfer. So anyway, that's the very brief overview. I should say this is joint work with a number of people: Ada Jan, Tina Chen, Bontingson, and Xiao Hong. Now, the actual attributions are a little bit more complicated, but all of this involve different points. So I want to start talking about the sort of the origins of the stuff I'm talking about. Now, so this is a sort of a very brief summary of what you know about continuous quantum walks. So a quantum walk has a state, and you have a classical quantum walk has a state, and you have a transition matrix, and you apply the transition matrix state, and you get a new state. And if that's not interesting, you keep doing it again, and so you get a long-term behavior, which is interesting. In the quantum case, it's, well, we have states and we have matrices which apply to states, but there's no sort of average long-term behavior. Anyway, for quantum walk, the states are n by n density matrices. So these are positive semidefinite matrices with trace 1. Okay, so this is one of the physicist definition of a quantum state. Now, everything we're doing today will be finite dimensional. Okay, so just positive semidefinite trace 1, that's a state. Now, how you actually realize a state experimentally may be a lot of a grief for the experimentalists, but we don't have to worry about that. And the transitions, so you want to change from one state to another. The only operations you're allowed to apply in quantum mechanics are unitary operations and measurements. And that's all I'll be saying about measurements today. So you apply unitary operations. Now, the unitary operations, in the cases we're concerned about, will be given as exponential. Oops, why isn't it doing that? Will be exponential of ITA. Now, this matrix will be called the Hamiltonian, or is called the Hamiltonian by the physicists, has interpretations in terms of energy. For us, it's going to be some sort of adjacency matrix for a graph. The important thing is that A should be emission, and for us, it's actually going to be real and symmetric in all cases. So we have our transitions and our states, and then if we have an initial state, then at time t, the state, which I'm going to sometimes call d of t, is given by this expression. Now, notice that this tells you that d of t is similar to d, and so d of t has got trace 1, and d of t is going to be positive semidefinite. So this is in density matrices to density matrices, as it should. Okay, and so we have this system, we have our initial states, we have our transition operators, and we're trying to get information about basically about, one way to think of it, you might ask, if in an initial state D, I've picked my Hamiltonian, what states could I reach? Okay, now, so the nice thing about this process is basically you turn it on, then you stop at a certain time. So you can go and have a cup of coffee. You don't need to monitor it. You don't need to change parameters during the course of things. So in other words, it's a constant coefficient difference equation. Now, most of the work on continuous walks takes A to be the adjacency matrix of a graph and uses these vertex states. So let's call them D sub A. This is the standard basis vector indexed by the vertex A. Okay, so this is the EA transpose. So it's an n by n matrix or D by D matrix with a 1 in the A position on the diagonal and 0 everywhere else. Now, physicists would write this in terms of their bracket notation, and I've put this here just to prove that I'm bilingual, but I won't be using bras and kets at all. Okay, so but these are as I said, the usual continuous walks use the adjacency matrix of a graph. Now, this is all set up by the physicists, but they take the adjacency matrix of a graph, and they take what we might call vertex states as the initial states. Yeah, actually the first couple of papers on this topic, they were using Laplacians rather than the adjacency matrix. I'll come to that in a moment. And then they changed over to using the adjacency matrix. I never saw any discussion as to why. And to a certain extent, it doesn't make a huge difference. But anyway, we'll come back to that. Now, so what other matrices can we use? The ones we're going to talk about today, we start with a diagonal matrix of valencies of X. So the I entry of delta is the valency of the I vertex. And the choice of Hamiltonian, well, two natural choices or obvious choices. One is the Laplacian, and the other is the so-called signless Laplacian. I'm not sure what letter people normally use for that, but we won't be saying much about the signless Laplacian, so the question mark will do. Now, in fact, you can, in a certain sense, the Laplacian, the adjacency matrix of signless Laplacian lie in a family. You can take more or less any linear combination of delta and A and get a valid Hamiltonian. Okay. Now, it's a good question as to how much things differ. To a first approximation, there's not a lot, but there are differences. They're not, so unless the graph is regular, of course, in which case they all give you the same information. Now, if we're using Laplacians, if you're using Laplacians, if you have a graph, an adjacency matrix, and you delete a vertex, the eigenvalues of the vertex deleted, and you say you delete the ith row in the ith column, the eigenvalues of that matrix interlace the eigenvalues original. So in a sense, adding a vertex is a rank 1 update. That's nice, makes your life simpler from time to time. Now for Laplacian, adding a vertex is not really, it's a bit more brutal. And in dealing with the Laplacians, it's more natural often to think in terms of adding and deleting edges. So if you delete an edge from a Laplacian, you get interlacing. Okay, if you delete a vertex, you don't. So there's an argument for thinking about edges. And so I'm going to define what we call pair states, the AB, which are just, so this is just a vector with a 1 on the A position, a -1 on the B position. It's a column vector. This is a row vector. So this is a D by D matrix. Now, because it's of the form XX transpose, it's a rank 1 matrix, and the physicists will call it a density matrix of rank 1 at pure state. Okay, and generally they prefer to work with pure states. It's just you don't often have the option when you're working with quantum mechanics, finite dimension, with quantum computing. So the point is we can associate a pair state with each edge. Now, why do I have to choose the sign there? Well, if I do this, I can see that the Laplacian in my graph is a direct sum of pair states. So it's just a sum of pair states, 1 for each edge. So since a Laplacian is a sum of pair states, it seems natural to use this as our initial state. Now you could say this is probably a signless pair state. You could have the unsigned version. In that case, I'd suggest you would use the unsigned Laplacian. Okay, and so there is an analogous theory, which I'll say a little bit more as we go on. So the Laplacian is the sum of the pair states of its edges, and because of that, it seems natural to use this as our initial state. So now we're in a situation, we're going to, now I'll be talking about the states. I should say, the understanding here in this situation is on this setup, I'm going to use the Laplacian as my Hamiltonian rather than the adjacency matrix. Okay, so this was a setup and it seemed interesting, and so I dumped it on Tina for a math thesis, and well, she has a lot of stuff in there, some of which I'll be talking about as we go on, but she worked out, we had a theory dealing with the vertex state transfer and the adjacency matrix, so various concepts and things, and so we could work reasonably nicely with the vertex state transfer, and Tina extended that theory to the Laplacian and also to some extent to the unsigned Laplacian. So she extended all that, and so we'll leave it at that for now. So she did it. Now the interesting thing was, the way I set it up and the way we thought about it, it's natural to think, well, I want to get transferred from one state to another. Then when I'm doing the vertex version with the adjacency matrix, I'm transferring vertex to vertex. And so the natural thing to do and the obvious thing to do is to think about transferring edge to edge. Okay, that's fine. That's what we looked at. And then about 2 weeks before a thesis was due to be submitted, it occurred to us that in principle, you could have transfer from a pair state on an edge AB to transfer on a pair state CD where C was not adjacent to D. Now, I tried fairly hard to prove, not for long, but I did try fairly hard to prove that couldn't happen. And then Tina did some calculations and discovered you can get it. So this is the smallest example that Tina found. So there's a 6 vertex graph there, and there are 2 pairs, one of which is an edge, one of which is not. And there's pair state transfer from the first pair to the second. Okay, so that meant we, when we wrote our paper, I think we called it pair state transfer. A thesis still went in as edge state transfer. That's all right. But see, the point now is we're not just transferring edges to edges. We're transferring sort of an arbitrary state to an arbitrary state, and so there's a more general thought coming along. So a state is a positive semidefinite matrix of trace 1. Now the Laplacian of a graph, what's going on here, is positive semi-definite, okay, for free. And so if m's number of edges in the graph, then 1 over 2m times Laplacian is a state, which we'll call a Laplacian state. And so, of course, if in the 2 by 2 case, this would just be what a pair state. And so now we have a project to investigate transfer between Laplacian states using Laplacian as a Hamiltonian. So we have an entire project, and so the point was, once we realized that you didn't have to send edges to edges, you now start thinking about the more general question, and it's a valid question. So the idea now is, see, with the continuous walks on the vertices, we're thinking of moving a vertex in the graph to the vertex in the graph, and originally we were thinking of moving an edge in the Laplacian, an edge in the graph to an edge in the graph. But I realized that we could equally well be thinking about picking 2 Laplacian states and asking when we can get transfer from one to the other. So anyway, we have a more general class of states, not just pair states, not just vertex states, but Laplacian states. Now, one reason this is interesting is because, as I said, physicists like pure states for various reasons, but the Laplacian states in general are not pure. And so you can hope to see some of the differences that being pure makes. Any questions at this point? Just like my lectures. Now, I should say that there's a Severini's got actually 3 papers on this, but it's a paper by Brownstein, Gosh, and Severini, who studied the Laplacian as density matrix. There are also interesting questions about entanglement, but I won't go into that at all. So, and this was back in about 2008, or maybe even earlier. And so it's back at the start of continuous quantum walks. And so they were looking at this question. And I found 3 papers on that. So what I've done now is I've in some sense attempted to explain how we got to this problem. Okay, so now when I talk about some of the theory that we developed to deal with it. Now, some of this was in Tina's thesis, and some of it we extended later on in. I'll list the papers in a little while, but so it's extended. So again, there's a group of us working on this, and different sets of us worked on different papers. But so I want to talk about some of the theory. As usual, the most important tool is the spectral theorem for normal operators, or the spectral decomposition. So since the Laplacian is symmetric, it's got a spectral decomposition. And in this case, I'm saying L is lambda r FR. So as my spectral decomposition. So these are idempotents. Their squares are equal to themselves. FR times FS is 0 if R is not equal to S, and the sum of the FRs is the identity. Okay. Now, because the Laplacian is positive semi-definite, these eigenvalues are non-negative. And the idempotents are real and symmetric. Okay, so we have that. Now, the point about that is, of course, that we can, once we have the spectral decomposition for L, we have a spectral decomposition for any reasonable function of L. So particularly, we get a spectral decomposition for U of T. Now, actually, I don't think I wrote it down, so I'm going to write it here. So we get that U of t would be sigma e to the I t lambda r f sub r sum over r. So the only thing that changes the form of the eigenvalue is the idempotents stay the same. So we have a spectral decomposition for the transition matrix. And this is very important in theory. It's also useful in practice because numerically you can compute this. Okay, more precisely, you can compute the idempotents and and the eigenvalues. So you can use this to investigate things computationally. So now the first thing has happened. Well, we have actually I should have. If we're dealing with state transfer, so we're having transfer from state D1 to a state D2, well, we might slip up and allow D1 to be equal to D2. Now that can happen. So you may find that you start with a state D and at time t, d of t is equal to the original t. So you've got a periodic walk. Now this is something that can't happen in any interesting case in the classical case. Okay, the walk is not converging any long-term state. Now the basic fact is that if I get transfer from, well, let's leave it for now. So we have transfer from real state D to real state D2 at time tau. Then D1 and D2 are periodic. Actually, I'm all right. D1 and D2 each periodic at time 2 tau. So if you're getting from D1 to D2 at time tau, if you go for another period of length tau, you're now gone 2 tau, you're back on D1. If you start on D2, you go via D1 back to D2 at time 2 tau. So this is somewhat unexpected. It's occurring in fact because the Hamiltonian is symmetric and not so U of t. Sorry, because U of t is symmetric, okay, and not just unitary. Okay, so and the other point about this is that it's in some ways easier to work with periodicity than to work with questions about transfer. So if we're looking for examples of graphs where there's transfer, we would normally try and find periodic graphs first and then check whether this periodic graph is admitted transfer. So it's a technical, interesting tool in the various ways. And the argument's quite simple. If you don't write this in density matrices, you can make it look a lot more complicated. So I'm going to assume that we have transfer from D1 to D2 at time tau. And we can test how long before tau turns into a t, but we'll leave it at that for now. So we're assuming we've got transfer from D1 to D2. And now we've got this expression for U of tau. And so when you wrap it around, you get this expression for D. So you've got e to the it difference of eigenvalues. And then you've got this little mess here, the FR D1 FS. So you've got a linear combination of these things. It's hiding in the background, but these matrices here, if they're not the non-zero matrices of this form, are linearly independent. I won't be using that explicitly. And so it is worth remarking that I'm not assuming that this is not zero. So when you're playing with a quantum walk, it depends on the spectrum of a graph, but it needn't involve the entire spectrum. In fact, generally it won't. Okay, only some of the eigenvalues are involved. In particular, it's the eigenvalue such that this is not zero. And we'll give that a name shortly. So from this expression, I'm multiplying the left by f sub k and on the right by f sub l. Now I do the same here and here. Now f sub k times fr is 0 unless r is equal to k, and f sub s times fl is 0 unless s is equal to l. And so we get this equation that this is equal to this. Now, at the moment, we're assuming, go back to it, we've got a real state D2, and our Hamiltonian is real. So the idempotents are real. States are real. So all the matrices inside are real. The only thing which could mess things up is this. Well, we've got this equation, so the implication is that this must be real. Okay, and if it's real, it's equal to plus or minus 1. And then it occurs to you, well, if it's plus or minus 1 at time tau, then at time 2 tau, it's the square of plus or minus 1, so it's 1. And so that's how you get back to your initial state. So, and the point about this is I don't need to, I haven't really assumed much in the way of properties of my state. I've just assumed that the matrix is real. So it turns out that a lot of the theory of continuous quantum walks between vertex states can extend without any real effort, that's a bit of a pun there, without significant effort, to the case where the densities and the densities are real. Okay, so, but the other upshot of this, well, there's a couple of things. The first is that the if we do have transfer, which is what we want, we're trying to transfer to an interesting state, then we will often get for free periodicity, and periodicity can be easy to work with. So let's leave it at that. Now, the other thing is that we have this condition, as I said, the only eigenvalues that matter, or the only things that matter, the eigenvalue is theta r and theta s, such that this is not 0. If it's 0, we just throw it away. We don't see it. It's not a problem. So we have some terminology here. So we say two states are strongly cospectral. If for each k and l is such that this is not 0, we have this relation with gamma complex of norm 1. Okay, so this is a definition, and it's for you guys that will seem completely unmotivated. All I can say, well, and in a certain sense, it's only been the official definition for a fairly short period. It's fairly clear to how to define, first we define strongly spectral in a case where we're looking at walks between vertex states. And that is simpler. And so that definition, in fact, we could do it for pure states. It wasn't clear what the right definition was when you got to states that weren't pure. And I had an idea, but basically Xiaolong's convinced me that this is the right definition to use. Okay, so they're strongly cospectral if this crazy condition holds. Now we've effectively seen that if we have transfer from one state to another, they're strongly cospectral. So strong cospectrality is a necessary condition for vertex state transfer. And since we can compute the idempotents, we can actually determine when two things are strongly cospectral. So it's a test it's a necessary condition for state transfer, and it can be used on the computer if you need to. Now, the set of eigenvalue pairs theta r, theta s, such that this guy is not 0, we're calling the eigenvalue support of D. Now, when you're dealing with vertex states, both these definitions become a little simpler, but they're both special cases of this. So if the states are pure, you can simplify this, but I won't go into that. I'm going for time. Lots of time. So, yeah, and this is something what I said, that strongly cospectral states have the same eigenvalue support. And so if you have transfer from state D1 to state 2, they have the same eigenvalue support. I'm not sure if this helps. If you think of the vertex version, well, imagine I've built a graph by welding together little rods. So I've got junctions being the vertices in some form. You can think of it as being little spheres, and they're welded together by metal rods. Now, if I have this nice graph and I drop it on the floor, it's going to make noises, and the noise spectrum is, in a certain sense, just the spectrum of the graph. So if you sort of bash the whole thing, then the vibrations you see will be sort of coming from the spectrum of the graph to a first approximation. Okay, and that's the graph spectrum. Now, what if I take my fancy little graph and just carefully tap one vertex? In that case, what I'll see is essentially the eigenvalue support of that vertex. It may be that there'll be harmonics which don't appear if I just tap one particular vertex. So that and so it's the spectrum in some sense local to the state you started with. This comes up in operator theory as well when they some proofs of spectral theorem go along this route. But so anyway, there it is. Now I said periodicity is useful, and I'm about to give you the main reason. There's a condition we get that if our state is periodic at time tau, then, well, for R and S and K and L and the eigenvalue support, and K not equal to L, this ratio is rational. Now, in general, the eigenvalues of graphs are not rational. Since the adjacency matrix is an integer matrix, the eigenvalues are algebraic integers, okay? And it's generally true, and apparently it would be a consequence of the generalized Riemann hypothesis, if someone proved that most graphs have irreducible characteristic polynomial. Okay, so my point is that we're getting something rational out of the eigenvalues, and that's giving us leverage. Okay, it's not obvious why at this point, and I won't really be going through it. But the point is that we learn that this ratio must be rational. Now, it's worth making a comment when you're dealing with eigenvalues of graphs. You often see expressions, when you're working expressions bound on things, you often see expressions involving eigenvalue differences or eigenvalue ratios. And there's a reason for this, because generally speaking, you've got some matrix and you're interested in spectrum. It's just as easy to get the spectrum of 2A. Its eigenvalue is just twice the eigenvalues of A. So the interesting combinatorial properties may be invariant under scaling. And the other thing is, if you take your adjacency matrix A and add a constant to its identity, well, you've shifted all the eigenvalues, but again, it's not clear that you've changed anything combinatorially. So it's from that point of view, it's not surprising that you see ratios and differences turning up in bounds. And so here we've got both a ratio and two differences. Okay, so we have this. Now, so we want to prove this. It has some very strong consequences, one of which I'll get to in a moment. So I'm just running through the same calculations before. If we're periodic at time t now, not tau's gone, then we have this equation. Okay, before I had a d2 here and a d1 there, but now we're going from d to d, so we can drop the subscripts. So at times, if we're periodic time t, we have this. Okay, now I multiply on the left by ek and on the right by el, same trick as before, and you get this equation. Now, these two guys are equal. And so if they're not, well, it's the same thing. If it's not 0, then this must be 1. So if you get periodicity at time t, then x provide t eigenvalue difference for eigenvalues for pairs in the eigenvalue support, that must be equal to 1. So that means this is equal to, if you do it, so this is going to be equal, you're going to have 2 mkl by I. So the exponent's going to be equal to this for some integer mkl. Okay, and so we just take that. So I've written a different version here that 2 theta k minus l is equal to 2 pi mkl, where this is an integer. Go back to me. No. So we get this equation. And now we just take, well, we get 2 of these, one for K and L, one for R and S. We take the ratio of those, the 2's cancel, the pi's cancel, the ratio of the integers is rational, and so we get this expression on the left. Okay, so it's a nice short proof. So this condition in the lemma is referred to as the ratio condition, and I think it first appears by the paper by Spectral, Spilinsky, and Severini. And so it's a very useful computational tool. The one consequence here, which I'm going to give now, the proof of this involves there's an exercise in Galois theory. So one of the things I find interesting about this subject is that you're not just using linear algebra. There's various forms of number theory coming in, Kroneker's theorem, the Gelfand-Schneider theorem. So there's some non-trivial number theory appearing in consequence. Now I'm hiding all that now, but one consequence of the ratio condition is if the Hamiltonian of your continuous walk is an integer matrix, an adjacency matrix or a Laplacian or a sinus Laplacian, and your initial density is rational, for example, a vertex state or a pair state, then if D is periodic, there's a square free integer, and I've gone for delta here. I couldn't use D. This is not the matrix of diagonal matrix of eigenvalues of valency. So it is a square free integer delta. such that all differences of eigenvalues in the eigenvalue support are integer multiples of root delta. So we've learnt that the ratio of the eigenvalue distance is rational, and in consequence we get that the eigenvalue differences themselves are each integer multiples of square root delta, the sum delta. Now delta might be 1, that's all right. Okay, in that case the eigenvalues in the eigenvalue support, the differences are integers. Okay, and so this is a very strong condition, and the so I used that to prove that if you're looking at, there are only finitely many connected graphs with maximum valency k on which perfect state transfer occurs. So that's telling you that perfect state transfer is rare. Now we have infinitely many examples, we have lots of constructions, but the point still is there are only finitely many connected graphs which admit with maximum valency k, which admit perfect state transfer. And in fact, you can push this even further to infinite graphs of bounded valency. They don't have perfect state transfer either. So the point is, by taking that ratio condition and working through some number theory arguments, we deduce this result. So this makes it a lot easier to identify if we're looking for examples of state transfer. Then we pick our state and we look at the eigenvalue support. If it doesn't satisfy this condition, well, we can throw it away. So this is a very powerful condition. So you can run through and identify the periodic states by using this condition. Now, in many cases, we can strengthen this a bit. The general consequence is that the eigenvalues of each eigenvalue is the form a plus b root delta over 2, where a is fixed and b varies. We don't have any examples of perfect state transfer where a is not 0, but that's another story. So we have this condition, as I said, is very powerful. And now we've proved it under fairly general conditions. Okay, so we need integrality to derive the eigenvalue, the number theory, and the rationals. But I mean, most states the physicists do something like taking the all-one spectrum and then dividing by square root n. And so that's not rational, but the states that you're working with are generally rational. And our Laplacian states are rational. And a few comments here. The assertion that state transfer implies periodicity requires real states and a real Hamiltonian. The equivalence of periodicity in the ratio condition holds for general states. Okay, and similarly for general states, you get transfer from D1 to D2 implies D1 and D2 are strongly cospectral. Now, strongly cospectral is not enough because you also need the ratio condition, and you can be strongly cospectral without the ratio condition holding. Okay, so this is the summary of what we can do. Now, the stuff I've talked about here is holding for a very general family of states. In particular, it will also hold for all our Laplacian states. So now I want to talk about some of the results. And these results, to a large extent, won't involve the quantum walks. We start thinking about these things and trying to prove things. So you try and find, and the first challenge is to start trying to find examples. Now, as Tina found examples on of pair state transfer on Laplacian, and in some way it seems to be a little easier than finding vertex state transfer. Now, the results, this is more to give you the scale, Tina's master's thesis, and then there are 3 papers by various subsets of the authors, and there's a fair bit of work there. There's about 75 pages, and I think this is already on the archive. And where's Xiaohong? This is about to go on if it's not there already, and I should get my ass in gear and get that up. But so the point is that there's a fair bit of work gone into this, and it's spread over a large part of our group. The machinery I've been talking about is largely in full, and there's a version of it in my paper on real state transfer. So as I said, Tina did find examples of pair state transfer by doing a direct computational search, but it's nice also to get be able to construct things. And so I'm going to try and find examples of pair state transfer. Now, the obvious place to look is in strongly regular graphs, because you would think if you get transfer between 2 vertices in a graph, those vertices must be cospectral. In fact, they must be strongly cospectral, which is a linear algebra condition on them. So they're forced to be similar. So it follows very quickly that if you get transfer between two vertices, they must have the same valency, for example. Okay, so so you expect, if I'm looking for pair state transfer, I would think that my the obvious, and I'm thinking in terms of edges, the obvious place to look is in strongly regular graphs. Now, of course, you might ask, what if you take an edge and a non-edge and start asking about that? Well, I don't have an answer to that. Something to think about. The theorem is if D1 and D2 are strongly cospectral pair states, then your strongly regular graph is just either a number of copies of K2 or the complement. So that's a so-called imprimitive strongly regular graph, and generally speaking, we're not interested in them. And the point is, we know these examples are trivial in a certain sense. We know about them already, but even if they weren't, so if they're strongly regular graphs aren't going to help us. Now, this is a bit less of a surprise because in a strongly regular graph, any two vertices are cospectral. When you delete them, the graphs left over are cospectral, but they're not strongly cospectral. And so in general, you do not get PST on strongly regular graphs. Or precisely, if the strongly regular graph is imprimitive, if the graph and its complement are connected, then you do not get perfect state transfer, despite the fact that the vertices are very similar. Okay, so this is, this is what it is, as they say. Now, now we're getting back to the Laplacian states, the more general question. So now I should say this is all very much work in progress. The problem is now you start looking for examples of transfer between Laplacian states of this form. Then you're going to have to go through it and pick. You've got some graph on 10 vertices, and now you're going to pick all the graphs with 5 subgraphs with 5 vertices. You suddenly realize you've got an awful lot of computation to do. And there are lots of graphs on 10 vertices. So computation is a bit of a mess, and I guess we're all sitting back hoping someone else will do the dirty work without success so far. So we're now considering Laplacian states. Okay. Now, one obvious comment is that if we get transfer from D1 to D2, then D2 is U, D1, U inverse. So they're similar. So in particular, that means that these matrices, if we get transfer from one to the other, must be similar. Okay, well, that's a strong condition. So that's doesn't help you much computationally, because you still got to, that just means you've got to compute the argument is this and that, or the character polynomial is this and that. It also follows, this is something that comes up because we're thinking more general states. We didn't really see it in the vertex stuff. If you subtract D1 from LX and D2 from LX, you get transfer between those two states. Okay, and so they must be similar. Okay, so the point is that we're trying to get transfer from Y1 to Y2. We're only going to get that if we also simultaneously at the same time get transfer from L minus Y1 to L minus Y2. Now, first thing is notice that Y1 and Y2 are not integer matrices. So this is a bit more complicated than we'd like. It's going to be matrix spatial entries. Okay. If it's just an edge, you're okay. But I mean, well, no, even then, the pair state, I was being lazy, is really half EA minus EB times EA minus EB transpose. So that you've got to make trace one. But actually, if you get transfer from the, sorry, I'm dithering. If we get transfer from the pair states properly normalized, we have properly scaled, we also get transfer between the unscaled pair states. And so, so we can assume that this is actually Laplacian of a subgraph. But the trouble is when you subtract this from LX, it may no longer be a Laplacian. It won't be a signed sum of the densities corresponding to pair states. So it won't be a sum of densities corresponding to pair states. It will be a signed sum of densities of Laplacians. And so you find yourself dealing with signed Laplacians, but we won't go there. So okay, so we have, the point is we have to be cospectral, but this also leads to another concept. in general, so I may take a Laplacian with 3 edges and a Laplacian with 4 edges, and then I have a normalized 1/6 and 1/4, and discover that there is transfer. And so what we're getting is that we're learning not that the Laplacians of y1 and y2 are cospectral, but the Laplacian of y1 is cospectral to some scalar multiple of the Laplacian of y2. Now, no one had ever thought about this before, I don't think. I don't know reference of it. Well, I mean, why would you bother? And when I remember the first time I was talking about this in our seminar, I was quite confident that if the two things were cospectral, the constant had to be the same. And then I started on that, and I started getting some anxious looks from the audience. And then we started thinking about it, and we realized, no, we couldn't see why it had to be true. And so then we did some computations and found, no, you can get cospectral. There are examples where the Laplacian, scale Laplacians are cospectral. This is an interesting question. No one had, as I said, no one had thought about this before, but you talk about graphs being Laplacian cospectral, but you can actually have them being scaled cospectral. And so so we have scale cospectral. So the normal case when two graphs are Laplacian cospectral, the scale factor is 1. But in the case where we're using our density matrices, there's a scale factor, which is number of edges in the first graph divided by number of edges in the second graph divided by the number of edges in the first. So there's a scale factor, and it's not obvious that can happen. And here's a badly drawn drawing of a pair of graphs which are Laplacian cospectral with a non-trivial fraction alpha. And well, Xiaohong found a bunch of these. By computation, it's easy enough to see that the graphs must have the same number of components, because the multiplicity of zeros is large is the number of components. The raises an obvious question: is are there connector graphs that are Laplacian ratio cospectral but not Laplacian cospectral? The examples we have are all unconnected. All disconnected. The problem is, if you're playing with Sage and you've got time for coffee break, you can generally run to graphs on 9 vertices, and that may not be big enough. And so you're seeing a fairly small sample. The spectral behavior of small graphs tends to be a bit atypical, so it's not clear. And you could, I don't have a strong opinion either way. It would be nice if you could prove that if they were connected, they had to be just Laplacian cospectral, but it wasn't always nice. So if we want to make more progress on this, going, it would be useful to have a wider range of examples of cospectral subgraphs. And so thinking about this led to the following. And so this is a somewhat surprising result. So if E and F are edges in a strongly regular graph, then the adjacency matrices of X drop E and X drop F are cospectral with respect to the adjacency matrix, the Laplacian, the unsided Laplacian, and the normalized Laplacian. Now, I know people talked about looking at graphs that were simultaneously cospectral and Laplacian cospectral, but I wasn't really convinced there was a lot of point to it. Brendan McKay had a construction, which I'll come to, which gets all these things. But so the point is, take a strongly regular graph, pick one with no automorphisms to make your life a little easier. I'll get to that in a second. And lo and behold, you're getting these things being cospectral with respect to each of these matrices. Now, that was a surprise. I knew about the adjacency matrix part, but the rest of it I might have known about Laplacian, but the rest of it wasn't known, didn't know at all. Now, this is already something. In fact, we actually proved a more general result. The first assumption is we don't need X to be strongly regular. We only need to be so-called one walk regular. Now, walk regular means that if you take the diagonal entries of A are constant for all K. So C there would depend on K. And one walk regular says that equals. So in terms of walks, it says that the generating function for closed walks that start at a vertex and finish at a vertex is independent of the vertex. And the generating function for walks from a vertex U to an adjacent vertex V, again, does not depend on the pair of vertices you choose, so long as they're adjacent. So you have this form of regularity. So strongly regular graphs are one walk regular. But any arc transitive graph, for example, is one walk regular. And so there are lots of examples. And then the theorem is that if C1, if you have two cliques in a walk regular graph, and Y is some graph with the most C vertices, then you can delete the edges of Y from each of those cliques, and you get a pair of graphs which are cospectral with spectral all those four matrices. So, it's happening more. And okay, for a strongly regular graph with parameters, one of the Latin square type parameters, with no automorphisms, Xiaohong got a set of 150 pairwise non-isomorphic graphs, any two of which are cospectral with each of those four matrices. Okay, so I mean, and so this brought us to the following definition. We say two graphs with adjacency matrices A1, A2, and degree matrices delta 1 and delta 2, a degree similar if there's an invertible matrix M such this is true and this is true. So you want them now. So that's the definition, and it's fairly obvious. If two graphs are degree similar, then they're cospectral with vector each of those four matrices I gave you before. That's an easy exercise. Now, Brendan constructed pairs of non-isomorphic trees that are cospectral with vector all four matrices. Okay, but he also proved that degree similar trees are isomorphic, which is a nice result. And so, so that tells you that being degree similar is stronger than having those four matrices cospectral, which is not obvious in advance. And we also proved that if the graphs don't have isolated vertices and they're degree similar, then the Ihara zeta functions are equal. So you're getting a fifth polynomial. And so this leaves us with an obvious question. If X is strongly regular and E and F are edges in X, X drop F and X drop F degree similar. Now we haven't had the courage even to do some calculations, but so that's and the other point I want to make is that all these, the thoughts here about degree similar and all these things are arising in consequence of the work on continuous quantum walks. Okay, but this idea of ratio cospectral Laplacians and this questions about degree spectrality are graph theoretical questions, spectral questions arising because we were thinking about quantum walks. And I'll stop there. Thanks for your attention.
Thank you very much. Are there any questions? Okay, so if you have the graphs that are cospectrally with Laplacians with coefficients, not with coefficient 1, do we know anything about cospectrality of the adjacency matrices?
No, I think you're the first to ask.
Okay, that's good.
If you look at the paper, there are examples in there, and they're certainly not cospectral. But
well, if they're not Laplacian cospectral, then they shouldn't be.
So they're ratio Laplacian cospectral, but they're not. Yeah, but I mean, well, as I did say, this is largely work in progress. Except that we weren't progressing much. I mean, the original work was done about 3 years ago, and we've finally got around to getting some of this written up on the archive. And as I said, we haven't had I haven't been able to convince a student to do the dirty work yet. How busy are you, Maria?
I'm so busy. Oh, there's so.
That's what I thought. I wasn't going to ask you.
Well, otherwise, you would have already asked me.
No, there'll be other things. I'm just teasing.
No, I don't mind. I mean, I can find time if there is need.
Yeah, I said I better.
Romy has her hand raised. I don't know if she's
in front of her face.
Oh no, I'm not volunteering. But I have a question.
Yes.
So for the vertex states, Chris, you're interested, for instance, in PST. You'd like long distance vertices. You'd like to find vertices in PST that are like, far apart. So how does that translate here? So for example, if you now extend to say pair states, how would you now incorporate the idea of vertices being far apart? Because that kind of breaks down.
I'm not sure that I agree with your intuition. I mean, what happens if with the cube course that you're getting PSD between vertices are a long way apart? And I guess with the examples on PSD on distant regular graphs, that tends to happen. But the issue is that the cube case is a bit special. We have lots of other cases where you're getting over a fairly short distance. And in a sense, the question that Gabriel asks is that, okay, I want to get transfer between two graphs, between two vertices a certain distance. What's the minimum number of edges I need in the graph? But so I think that, yeah, okay, that's a response to your question, but not an answer.
Okay.
Oh, I guess the other thing I should say is I got no idea what the distance between two Laplacian states would be. What would be the right measure of distance? I mean, yeah, that's a second thing. I mean, I'm not saying there isn't one. I just don't have any idea in mind.
Okay, any more questions?
Do you have examples of, say, two strong regular graphs with the same parameters, delete an edge from each of them, and still have cospectrality with respect to all the four matrices? I'm just curious how much
Hey,
of
your name's on this paper.
here too.
I would have to. My immediate reaction should be that it will only depend on the parameters. Sharon may have an opinion if she's brave enough to raise her snout above the trench, but I suspect that the graphs are different. You have the same parameters, then certainly the edge-deleted graphs are cospectral in the ordinary sense, and probably in the Laplacian sense too, I think. But basically you just need to go back and look at the proof. But I haven't thought that particular question, but certainly if you've got two strong graphs the same parameter, then the vertices in one graph are cospectral to the vertices in the other. So X and Y, and I think that's true for edges. Now I haven't thought about the other matrices. But it should be fairly easy to see from the proof if you're using more. I doubt that you're using more than parameters. I mean, what other information do you have about your strong regular graph? I mean, that's, you say that a strong regular graph has got those parameters, and at that point, the structure of the graph tends to disappear. But I'd have to go back and look.
Okay, so besides many things in the chat, there is a question.
Well, it's okay. So the question is whether, what do you mean by PEST? It's not clear to me. But you could certainly ask the question. I mean, I was talking about strong regular graphs because they tend to be the first thing that come to my mind, but certainly you could think about asking the same questions on the K graphs.
There's Roshana is saying that PST means perfect edge state transfer.
Yeah, that's what I thought, but I wanted to make sure. Yeah, and it's not clear. I don't remember what Chow was using for his states. But there's no reason why I can't use pair states or Laplacian states as my states and the adjacency matrix my Hamiltonian. There's nothing that stops you doing that. I was trying to explain how I got to the problem, and so we were thinking about transfer between edges. We didn't realize we could get a transfer between more general things. Now, it's clearly you can mix things up. You can, as I said, you could take Laplacian states and then just use the ordinary adjacency Hamiltonian. I had this vague feeling that using Laplacian was more natural, and we hadn't worked with Laplacian, so I thought it was worth doing. But there are other variants you could try.